Okay, good afternoon, everybody, and welcome to a new appointment of the Climate Finance Lectures, Workshop, and Webinar Series organized by Fondazione Enrico Mattei. My name is Gianni Guastella, and I'm Senior Researcher here in FIM. And virtually connected with me today, I have Professor Anastasios Xepapadeas and Professor Massimiliano Mazzanti. This series is part of the Firm and Cities Transition Towards Sustainability Research Program. This is one of the 4 research programs in FIM, and it's dedicated to topics related to the transition toward decarbonization with a particular focus on firms and cities. And it's coordinated by Professor Stefano Parelli. As usual in research programs, alongside research, we spend some of our time to organize dissemination events, which provide valuable occasion to confront between researchers and the general public, share ideas, and favor discussion on emerging topics that regard various aspects of sustainability. So far this year, we have hosted 2 webinars deepening the aspects of the Green Deal concerning the energy transition, 1 webinar about the EU Action Plan on Sustainable Finance, and 2 on how to measure sustainability at the firm level and the relationship between the environmental and financial performance of firms. We also hosted 2 workshops in the past 2 months, one about climate disclosure and one about the financial impact of climate-related risk. The event of today is the second of a couple of lectures by Professor Anastasios Xepapadeas. Professor Xepapadeas is currently Professor of Economics at the Athens University of Economics and Business, formerly was Dean of the Faculty of Economics and Lead of the Department of International and European Economic Studies, and also full professor at the University of Bologna. He is international member of the US National Academy of Sciences and is past president of the European Association of Environmental and Resource Economics and past chair of the board of directors of the Bayer Institute of Ecological Economics of the Royal Swedish Academy of Sciences. He has been editor of Environmental and Development Economics during the period 2005-2014, and currently he serves as co-editor and member of the editorial board for multiple journals, including Environmental and Resource Economics, the Annual Review of Resource Economics, the Review of Environmental Economics and Policy, the Journal of Environmental Economics and Management, and Water Resource Research. He has published more than 130 papers in leading journals, and he has participated as coordinator or lead researcher in more than 35 research programs funded by the European Union, the Greek government, or private sources in the area of environmental and resource economics. Today, Professor Xepapadeas is going to drive us into the discussion about the spatial aspects concerning environmental and resource economics. We invited Professor Massimiliano Mazzanti to discuss the topic at the end of the lecture. Professor Mazzanti is full professor of economic policy at the Department of Economics and Management of the University of Ferrara, where he also serves as director of the CERCIS, that stands for Circular Economy, Innovation and Small Medium Enterprises Research Center, and he's also director of the Inter-University Network SEEDS, the Italian Inter-University Research Center on Sustainability, Environmental Economics and Dynamics. Professor Mazzanti is among the leading Italian experts in the field of environmental innovation, environmental policy for climate and waste, and the study of the relationship between environmental and economic performances. Before leaving the floor to our speakers, I would like to thank Professor Parelli and FIM's staff for making this event possible, and also our partners, SAIPEM, A2A, ACEA, Cattolica Assicurazioni, Assicurazioni Generali, Unipol, and Utilitalia, who support us constantly in the dissemination activity. The timing of the session is the following. We plan to have a lecture presentation by Professor Xepapadeas of about 30 to 40 minutes, followed by 15 minutes discussion with Professor Mazzanti. There will be some space at the end of the discussion for questions from the audience. So thanks again, Professor Xepapadeas, for having accepted the invitation, and Professor Mazzanti for having joined us in the discussion. Tassos, the floor is yours.
Thank you, Gianni. Thank you. It's a great pleasure to be in FIM, even remotely. Hopefully, times will change, and then I will be able to be in Milan and give my presence. Let me start with the topic. Let me, so you can see my screen now. Okay. So as Gianni said, the discussion is about spatial environmental resource economics. And my idea is to cover the following topics. First, let me tell you that I need to put on the last bullet that this is work that have been done jointly with my very good friend and colleague Bas Brock from the University of Wisconsin. So what basically I'm going to present here for you are results and stuff that we developed together, along, of course, with similar results developed by other colleagues. So I will try to motivate the discussion and try to convince you and the audience that talking about space in environmental economics is important. And then I will try to go through the way that we model transport in space, the way that we perform dynamic optimization in space and time, the way that we study the formation of patterns in space. I mean, how would we see agglomerations, how we see concentrations, how we see clusters in space. And at the end, I will try to present a few applications from environmental resource economics and try to stress the policy aspect of this approach. So this is the whole idea. Now, space is basically a central feature in environmental resource economics because basically our environment is embedded in space, okay? And all the different processes and activities that take place in space. So basically we have air pollutants, okay, that are transported in the atmosphere, okay? We have heat that is transported from equator to the poles. We have resources that diffuse in space, that travel in space, that they move from one space to the other, from one area to the other through natural mechanisms. Now, in terms of the natural science, in terms of the aspects that relate to the natural science of the problem, the spatial dimension relates mainly to mechanism. Okay, scientists try to understand why objects move. Okay, what kind of mechanism makes them move, and what is the result of these movements. For example, in climate change, we observe, I mean, if you go now to one of these IPCC maps that describe the anomaly across the globe, you will see that in the North Pole, the anomaly relative to the pre-industrial period is something like 3 degrees, while the average anomaly for the globe is 1 degree. So this is polar amplification, and this polar amplification generates a special pattern in the temperature anomaly. If we go to biology, you see that animals have stripes or spots. Okay, this is a formational pattern. Again, if we go to pollution, we see that issues like the brown cloud is distributed in South Asia or over the Indian Ocean and has a specific structure in terms of space. Excuse me. Now, in economics, when we talk about space, the idea, and especially the idea about space recently, is to analyze everything in the context of new economic geography. Paul Krugman, which is among the top scientists, that among the most important scientists that, at least in the recent decades, developed these kinds of analysis, describes in one of his papers in the Journal of Economic Perspectives, gives the title of Space, the Final Frontier, which those of you that a long time ago was watching Star Trek, if you remember, the title was the same. So space in economics is also the final frontier, but in terms of an economic space, deals with agglomeration, clusters, and the way that spatial spillovers move around a certain geography and generates patterns. Also recently, we have a special growth theory that tries to understand how knowledge spillovers or capital movements could be fit in these models of space. Now, why we're interested in this? Okay, is there any reason? Okay, biologists are interested because they want to find out how the leopard got its spots. Okay, this is legitimate. But why economists? What is the importance of space in economics? Now, one basic assumption that we do in economics, and especially when we try to design economic policies, is that we assume that the spatial diffusion of an externality is infinite. Therefore, if I have an externality like pollution, if pollution is spread in space, is diffusing in space at an infinite speed, then everything is uniform. Okay, which means in terms of policy insights that my policy would be spatially uniform. I won't have different types of the same policy, different carbon taxes, different permit systems, different pollution taxes across different localities. Everything will be the same. However, in reality, diffusion is not infinite. This will generate spatial patterns. This will generate local scales with different shape, with different form than nearby spaces. Therefore, we might start talking about localized pecuniary taxes or cap and trade with localized characters, or the need to introduce additional instruments. So this is the whole idea. So what I will try to do the rest of this presentation is to try to bring out three main points. Okay, the first is to present models of spatial transport, how we model the transport in space, and then since in economics we're sort of obsessed with optimization, how we optimize in terms of time and space. The second point that I would like to make is to see how optimization in economics generates patterns. Okay, so when I optimize over time and space, and when diffusion externalities are present, how spatial patterns emerge. And finally, I would like to give some examples of optimal management and optimal policies when I have diffusion externalities and spatial spillovers. So this is, if you want, the motivation and the points that I would like to stress in this lecture. So let's start about modeling spatial transport. The most usual way to model things is what is called, we call it diffusion, and diffusion according to Fick's law. Okay, diffusion basically describes movement, okay, of objects, whatever they are. Could be living animals, could be capital, could be pollution, could be whatever is moving in space, something. Okay. Now, the most I would say a simple way to model diffusion is to use Fick's law, which states that the objects, the moving objects, move from locations of high concentration to locations of low concentration. Okay, so if my space is aligned, like this one here, okay, then what I have, if the concentration is high here, some of it moves in this region, in this part of space. I might have generation, suppose that this is a fish, okay? So this is an area, lots of fish, it moves to this area with lesser fish, there's some growth of fish in here, and then as the concentration increases, they move further down the line. This is one way to describe diffusion. Now, in terms of mathematics, following again Fick's law, this says that the flux of the material is proportional to the gradient, is proportional to the derivative of the concentration of this object, of this mass, with respect to space. So basically, I have this mass here, y, which is a mass, the fish, if you want, at time t and location x, okay, and the flux is proportional to this derivative. So this is diffusivity, okay, and the simplest case, okay, in the simplest case is described by this constant diffusivity parameter. Sometimes we call that linear diffusion. Of course, one can describe nonlinear diffusion processes. So, for example, if I have a material, let's call it fish again to make things simpler, which with biomass described at time t and location x, then the time evolution, rate of change of this mass at location x depends on the net growth of the mass plus diffusion, plus what comes from areas of higher concentration. The way that I put it here is to make it more clear in terms of economics, because basically the growth depends on the mass, on the stock, typical way that we model these things. And I put another parameter here, which will play the role of a control, since later on, as we will move to optimization, we would like to describe systems which are optimized. So this is the basic thing. And you might, I put here some graphs that indicate how the, you might see now the evolution of biomass in time and space. Okay, so this is time and this is space. You see here, I start from an area, from a structure which is almost flat. I mean, they have the same biomass in different points in space, but then the thing grows and gets a shape. Here I have two resources, one competing against the other, and both of them involved in space, and so on. Now, this is one way of modeling things. Another way of modeling things is to assume the following. Diffusion describes movement in neighborhoods, okay? It's local. So diffusion describes movements which are local. However, we also have long-range movements, long-range diffusion, where the spatial effects comes from far away. Typically, when we have situations where the spatial effects comes from far away, we tend to model these effects by this quantity here, which is an integral operator, which act on this function here, which is a kernel. Here basically says that the effect on a certain spatial point depends on what happens in the other spatial points, which could also be far away. And this is basically what describes the effect. The basic idea that the further out something is, the smaller is the spatial effect. So this is another mechanism, and this here is a kernel. You see that the effect is high. If I'm close, this is my location, but I'm concentrating. So if I'm close, the effect is high, and then the effect goes down. Sometimes could become negative. You might have problems which the effect becomes negative, and so on. And here I've put a graph where you have the reverse situation from what I had in the previous graph. Now I start with long-range diffusion from an initial point where I have pattern. You see, I have different concentration at different points of times, but I end up with a flat steady state. Another way to model space is the so-called metapopulation models. Okay, these models treat space as discrete patches. Okay, as discrete parts, and the idea is that I have movement from one patch to the other. So instead of modeling the movement by partial differential equations, like I did before, I model now these movements by a set of ordinary differential equations, but this term here describes what goes from I to j. Okay, so if here I have the concentration in the patch in the area I time t, this term here describes what comes from j to I, or what goes from I to j, depending on the different parameters. These models were the first to be used to model fisheries. Jim Weiland, his students, Ankiriko, Smith, that group there, used lots of these models, and they developed very neat, very elegant models of fisheries, which then they all they applied. They used empirical, used data, and they did some very nice empirical applications. Okay. Kernels also I could have in space. So basically, the ways that one could model movements could be either through linear or nonlinear diffusion, through long-range effects using these integral equations and the integral kernel, or using discrete patches and flow from one patch to the other. Now in economics, we're used to optimize things. Okay, most of our work goes around optimizations, trying to find the best solution to allocate resources and so on. Typically, in dynamic models of environmental resource economics, what we perform temporal optimizations. Okay, we optimize using optimal control methods or dynamic program methods. We optimize through time, trying to find paths that will optimize certain objectives. Now, when I introduce space in a problem of environmental and social economics, I need to optimize both with respect to time and space. So here I will give you an extension of the maximum principle, which is a standard tool that we use in economics to optimize for temporal problems. And basically here you see that my objective, what I do, I maximize my present value over an infinite time horizon, but then I add through this integral all the optimal values, all the optimal present values at each point in space. Okay, so basically here I aggregate over time and I aggregate over space. My constraints now change from ordinary differential equations to partial differential equation, because I could either include this diffusion term here, okay, or I can include this integral term here that will describe the kernel. So in terms of mathematics, the change in the formals of the problem is that now I have an optimal control problem, but which is constrained either by a partial differential equation or by an integral differential equation. There is an extension of the Pontryagin principle, which has been proved now in a consistent way, that says basically that if I have a path like that, now what this path says is an optimal path. So this is the optimal control that I apply at each point in time t and each location x. And this is my state at each point time, at each point of time t, at each spatial point x. So if such a path solves the problem, then basically my control maximizes the Hamiltonian function in the same way that we do normal control. But the Hamiltonian system now, it's a system of partial differential equations, okay, that describe now the movement of my state through times and space, but also the movement of my co-state in times and space. But since in our problems the state is stock is a quantity, and the co-state is a price, it's a shadow value, then basically 10 and 11 describes a price quantity system which results from an optimizing behavior in space and time. And this is kind of interesting because as I hope to show you later on as we move to the exams, this basically introduces of spatially dependent policies. Okay. Of course, transversality conditions, the temporal transversality conditions to infinity apply, and there are also technical boundary conditions in space, but I don't want to bother you with these things. Again, if my movement is characterized by these spatial kernels, the idea is basically the same. I extend the Pontryagin principle. My control will maximize the Hamiltonian function, and basically I have now a system of integral differential equations that will describe the movement of the state and the movement of co-state with respect to time. You see, the difference here is that now I have the integral term characterizing the spread of the price and the control system. Okay, so this is the technical part, if you want. Okay, but why is the technical part important, at least in economics? Now, one of the things that started the whole business, especially in terms of biology, is basically how, in an endogenous way, we might have the formation of patterns. Sometimes the word morphogenesis is used by biologists, which basically mean, it's a Greek word, means the generation of shape. How shape is created, but how shape is created through endogenously, through the mechanism that characterize the phenomenon. And of course, biologists were very interested in answering this question. Okay, how the leopard got its spots. That was one of the important questions in biology, and you can see this very beautiful leopard, and the idea is how these spots were created. How are these spots created? Alan Turing, in 1952, after he has made his contribution in computer science, published a very important paper, and he modeled the following thing. Now, suppose that I have two substances, a blue paint and a red paint, okay? And you put them together, and one diffuses into the other. Now, if the rate of diffusion is very fast, okay, if they move very, very fast, at the end, you're going to have some kind of a purple. You're going to get a unified color. But Turing discovered that if the diffusion, it's not that fast, then you're going to generate a pattern. You're going to have blobs of blue and blobs of red. Okay? And this is the famous Turing mechanism, also was called Turing instability, because basically it says that you start from something that is homogeneous, and that homogeneous shape becomes patchy, gets pattern. So that was the Turing instability, and the Turing mechanism has been used to explain these kinds of patterns. However, when we try to move Turing mechanism and this kind of analysis into economics, we see that there is a difference, because biology describes mechanisms, okay, but at least explicitly there's no optimization, okay. So what is relevant and interesting, at least for economics, is whether in an optimizing system I might have a similar behavior, okay. So whether pattern could be developed in a system which I optimize. So if I optimally control a system, okay, if I'm a forward-looking agent like a regulator, and I try to optimally control a system in which I have diffusive externalities, am I going to generate a pattern? Yeah. With my, as I said, with my good friend and colleague Bas Brock, we proved the result a long time ago now that indicated that if I have an optimizing system, okay, and I start from a flat Earth situation, okay, a situation where I have space, but everything across the space is uniform, okay, and then I perturb the system with diffusion, okay, then the optimizing system might generate patterns. It will not always generate patterns, okay? It's something that depends on the parameters of the system, but there is a parameter constellation, parameter space for which I will generate patterns. Okay. And the idea is that the patterns might be persistent, okay? So in a sense, an optimizing system might generate endogenously form. This is one of the results that we described, and here I will show you that this result depends on a lot of the discount rate. So here is what we call the Turing set. And the Turing set is the set of parameters in which you can have this instability and you can generate patterns, and this set increases with a discount rate. But what's the importance of that? Okay, the importance of this result is the following: that in an optimizing system in economics, I have states and co-states. States are quantities, co-states are prices. Okay, so this result tells me basically that an optimizing system in times and space under diffusion or long-term spatial effects might end up creating patterns in the quantity price space. And this is important because of the following. Okay, suppose that I have a situation where private agents ignore the diffusion externality. There is diffusion, okay, but private agents ignore the diffusion and ignore the externality, the way we always do in environmental and socioeconomics, okay? Then a regulator will come and will try to internalize the externality, okay? But since there is diffusion, okay, we might have pattern generation. Okay. In the same way, when the regulator will try to solve its own problem, the socially optimal problem, in which the regulator will try to internalize the spatial externality, the regulator might get either an optimal pattern or no pattern. So you might have a situation in which the privately optimal solution, which ignores externality, and the socially optimal solution, which internalize diffusion externality, end up having different spatial patterns. Okay? This implies that my policy would have a character that will depend on space. Okay? Because I would want the spatially different pattern from the private problem to coincide with the pattern of the social problem. And this basically introduced spatially dependent instruments. This is the whole idea. I will give you some examples in the last 4 or 5 minutes that we have. And this is an example from Sankiriko and Whelan about a fishery. And here I have fishing effort and biomass in different patches. Okay? And there is flow of effort according to the range in different patches, and also flow of fish according to natural mechanisms. Sankiriko and William find that the optimal instrument should reflect different the spatial structure of a problem. So we have instruments which emerge in space. Okay. This is another example from a patchy groundwater aquifer. Groundwater aquifers usually are not uniform, they're patchy. They have flows from one to the other, which basically is characterized by what is called Darcy's law, which is a law of hydraulics. And now, the result of this optimization problem, okay, which has the spatial externality here, okay, the result is basically that you need to define different pumping policies at different areas above the aquifer in order to take into account these spatial characteristics. Here is from a paper that I did with Bas Brock, where we had a model of a semi-arid system in which we have plants and water. And both plants and water move. Water moves underground, plants move and go to different places according to existing water. And we studied the myopic solution where the farmers do not take into account the externalities, and a social optimal solution, and the result was that we need to introduce spatially dependent policies. Okay. Same result have been obtained by Goetz and David Zilberman regarding pollution accumulation in lakes, and by though again here's Anastasios Xepapadeas, Goetz and Zilberman about stock pollution. The idea in all these examples was that once you allow for movement across space, and then you have an externality which is not internalized by private agents, then your optimal policy would be to introduce spatial characteristics. There are similar results that can obtain in different problems. I mean, I have here the lake problem that's studied again by Baz and me, and also by Carmen Camacho and Perez Barahona, and the results are always similar. I will finish with climate change, and I'm not going to give you the models because I don't see that we don't have much time. But again, when you explicitly introduce space into climate, either through pattern scaling with statistical models or through movement of precipitation and heat transportation, you end up with policy prescriptions that tell you that the carbon taxes should be different at different places across the globe. Okay? And I know that one of the arguments here is that if I differentiate carbon taxes across space, I might have carbon leakage and so on, which fine, I accept that. But nevertheless, the idea is that if you want to follow policies that sort of obey the way that the system operates, then you need spatially differentiated taxes. And this argument of spatial differentiation carbon taxes is not comes also from different, if you want, points of view. I mean, the recent discussion of the High Commission for carbon pricing again suggests that carbon taxes should be different across different parts of the globe. So my idea here, and I will go straight to the end of this thing before the thank you, is that what I tried to do was to give you the way that spatial methods, little by little, are coming into environmental socioeconomics, to emphasize that space matter when I want to design efficient policies, and whether these and how rather these policies will be applied in the real world, it may be a different story. But if you start from the main idea that space matters and you might need to have spatially differentiated or spatially dependent policy instrument, then you look at policy design from a different point of view, and also to indicate that spatial methods could provide some insights into other aspects of economics. As I said at the beginning, in Europe, there is a very fruitful discussion about space analysis. My colleague Fausto Gocci in Rome and Pisa has done lots of work with other colleagues in France about Pontryagin and other colleagues there, done lots of work on developing growth models, which space is explicitly included. And again, this sort of represents one way of looking at growth theory in terms of time and space. Okay, I'm going to stop here. Thank you for your attention, and I hope we have some nice discussion afterwards. Thank you.
Thanks to you, Tassos. Thanks very much for this very interesting presentation. I mean, I know that space matters, and personally have a background in spatial economics, economic geography, and spatial econometrics, and I know the meaning of your words, but personally, I was pretty enthusiastic to see how all this interest in space translates into something that may appear as very theoretical, but as in fact very practical meaning, I would say. But, sorry, Professor Mazzanti, the floor is yours for the discussion. I will leave my comments for the end.
Okay. Thank you very much, and good evening to everybody. Thank you for the invitation, and send my greetings to Tassos. Thanks for the excellent presentation.
Hello, hi. Yeah. Nice to see you, even remotely.
Yeah, warm wishes from Bologna, actually, because I'm in Bologna where I live. So I was thinking, I take the spatial dependent policy as the key word, also economic geography. I was thinking that when I was a student 22 years ago, at master's student in environmental economics, space was not really an issue. So it is nice that this space and geography have interacted with environmental economics over the past decades. The only issue I have in mind is that I was just preparing a lecture on the least cost theorem using the Baumol book, and the only issue in that environmental policy theory was the effect of efficiency. Equalizing the marginal cost of abatement through a tax or through the emission trading also means to reallocate abatement. So in that way, you had an implicit reallocation of abatement from high cost options into low cost options, that you could have the risk of having environmental hotspots, for example. So space was kind of an implicit issue, but not explicit. So so as Tassos was saying, things have evolved, and one key point is economic geography and innovation. There's been a lot. I talk about one of my fields about the fruitful interactions between innovation, regional studies, economic geography, and environmental economics over the past 2 decades, I could say, where you have innovation diffusion as one key issue. Innovation diffusion that can be delivered by policies. So policies have these spatial effects because they can generate even heterogeneous nonlinear type of spatial diffusion depending on the type of sectors, for example, you have in a given territory. On the type of specialization you have. You have studies at micro level using firms data, using regional data. You have a literature on policy spillovers at macro level. Using my memory, I have in mind some works by Valentino Bosetti, for example. There was a paper, talking about carbon taxes, a paper by Metcalfe and Stock presented at the last summer, I guess, in the American Economic Association, and talking about carbon taxes in Europe. And And the paper is showing that carbon taxes are not impacting on European GDP and employment. One main criticism, you have the discussion online on the site, is that the paper is not including spillover effects and I mean the fact that Europe is an integrated area. So in carbon tax effects can move around through geographical, contiguous effects just based on geography, but also through connection that are dependent on trade relationships. So you have the space is just space. In geographical terms, could be an economic space, which is represented by trade. It could be technological relations. So you see, all those things are now integrated in that regional studies, environmental economics, economic geography synergy. So I think this is really important. I also I've personally touched on spatial issues, working with a colleague Tassos knows very well, Anna Montini, because Anna is she's a statistician, applied statistician, and we have worked a lot on waste. And why waste? Because waste policies, especially in countries like Italy, Germany, federal states where the competencies are really decentralized, you have a lot of even weird spatial effects, in the sense that when the competence is really at the level of the province or municipalities, you may observe different distribution of policies, policy stringencies that then affect environmental performances. You can have imitation, so we have clusters of provinces and municipalities which imitate each other, and in the Italian system, for example, given that the environmental agency provides very good data, you may play with those data. We played with Anna, for example. We published a chapter in the Handbook of Waste Management some years ago, analyzing the evolution of clusters over time. So clusters that were not just north-south, in different clusters of provinces that were aggregating on the basis of environmental policy and economic conditions. So this is another aspect and field where policies are pretty relevant. Just to finish with other two examples, to share with you. One is a possible interaction in terms of research, because from my applied perspective, we are, for example, working on semi-parametric analysis of innovation, environmental innovation driven by environmental policies, and we are trying to endogenize the policy. And one factor is the typical R&D spillover. Okay, that so a country can innovate because of again of the relatedness to other countries. Here, the key seminal work is by V. Griliches in the Scandinavian Journal of Economics, 91, I guess, is in search of R&D spillovers, which is one of the nice paper to interact innovation aspects and environmental aspects. Well, one way could be again using more flexible semi-parametric analysis to put some geographical factors into the explanation of policy endogeneity. So this is maybe something that could be attempted, moving from the macroeconomic to the meso-regional economic level. I got your point about different carbon taxes. I in terms of policy implication, I could say that I don't know whether agree is the correct word, but it is a practical consequence and implication of a policy theory, I mean, having different even carbon taxes. I really finished because I just had this paper from colleagues, but I think you know Anil Markandia, a paper published in the journal Spatial Econometrics 2020 by Anil Markandia and other colleagues from Rome 3. Is about climate conflict vicious cycles in the African continent. It tries to integrate with refined spatial data and using a dynamic spatial model. It tries to integrate wars, I mean, and conflicts within the adaptation, the climate change adaptation issue. So integrating another overlooked aspect, especially in a continent like Africa. So the role of violence and conflict spillover, which could undermine the adaptation policies in a given area. So I think this paper is pretty crispy in terms of advancement. So yeah, so thanks again. I hope I provide a bit of complement thoughts then.
Sure, thank you very much. Well, I would like to see whether there's some questions from the audience. In this case, participants can use the GoToWebinar bar on the right, the question bar, to write down their question, and I will read them. Yeah, in the meanwhile, while we wait, thanks again for this very nice presentation. That was, on my view, just a quick comment. Basically, as also Massimiliano said, in the past 20 years, we have seen the emergence of a very wide literature investigating the spatial aspects related to economic growth, economic development, the environment, and other things. In my point of view, what much of this literature actually lacks is a theoretical foundation for the spillover, because it's very easy to say, look, this is the effect of spillovers. When you simply look at the spatial distribution, because basically you look at the geographical distribution of the map or something else, and you see, look, there's a lot of concentration of a specific variable or other things we're looking at, and this is the result of spillover, likely. So that's why we need to, in applied works, to take into account this kind of spillover effect. But in my view, I would say that in the majority of cases, such a spatial concentration can be seen as an optimal equilibrium allocation of the variable, and in this case, it should be more interpreted as a kind of spatial heterogeneity. Okay, so basically the idea is that things do not really need to be evenly geographically distributed in space. So we can have spatial concentration for a variety of reasons, and this is not necessarily evidence of spillover effect. So the final message is, it's good to have theoretical foundation for the spillover effect, because so many times we look in applied works for the spillover effect when in fact we don't have theoretical foundation for that. And it's possible that we miss that and we confound the spillover effect with simple spatial heterogeneity. This is what I found in many of the papers that also Massimiliano mentioned about innovation and R&D dynamics and so on, and also in other papers about about environment as well. Is there any question? I think I can see one. Tassos, can you read the question?
Where is it?
It's on the right.
I don't see anything.
Yeah, now me neither, but now you should see, but I cannot anymore.
I don't see any question. Should be on this panel, right? On the control panel.
Yeah, it should be on the right, but I think Ricardo is now sending the question. Okay, I'm gonna read the question. Thank you very much for the nice presentation. How important is, in your opinion, the modifiable area unit problem? And how do we choose the right unit of aggregation for each problem? Very relevant question. Thanks, Giacomo Falchetta, for making the question.
How do I define what problem?
How important is, in your opinion, the modifiable areal unit problem? MAUP problem. How do we choose the right unit of aggregation for each problem? Thanks.
I guess the unit of aggregation is in terms of space, right? I guess.
Yes, exactly.
Okay, I think it's an interesting question, because also depends what Massimiliano mentioned a little before, because you might have, depending on the problem, the topology could be geographical space, and typically you might measure from distance from capital to capital, or do something like that do it in spatial econometrics. But there is also this concept of economic space. Okay, there are some papers there that, and this is important, because, for example, if you consider the way that capital moves, okay, capital moves different than fish, because fish could go from an area where there is lots of fish to an area, nearby area, where there's less fish, okay, and there's resources there. So you have local interactions, but capital moves from does not move in a local way. So there was a few papers that were discussing economic distance. So the unit was, say, transportation costs. And in that sense, I don't know, United States was closer to Australia than United States, I don't know, to Central America. So you might need, you might have to define the area, the unit of measuring your space in a different way depending on the problem. And this is what Massimiliano also hinted in its discussion about the European Union and the way that you describe distances. So you might have geographical distance, or you might have economic distance. I don't know if I answered the question.
I guess so. Okay. Is there any other question? Okay, I see no other question in the room. So I also think we are running a little bit out of time with respect to our schedule. So once again, thanks very much, Tassos, for having joined us.
Thank you for the invitation. As I said, it's always a pleasure to see friends and
I really wish we could make it in presence next year.
yes, we should. I mean, hopefully we'll get this vaccination and then everybody might be able to get close to everybody else without having these problems. Anyway, I'm stuck in Athens. You're stuck in Bologna, Massimiliano. You're in Bologna, right?
Yeah.
Gianni, where are you?
In Sicily.
Sicily, so.
Yeah. Okay, thanks very much again. Thanks both for taking part in this week.
Bye. Great.
So.
Bye.
Ciao. Ciao.